When we talk about logistic regression, the primary characteristic is that the dependent variable is binary. And so because it's binary, the slope that we get from the regression equation does not show a unit increase in the dependent variable, or does not show an increase in the dependent variable with a unit increase in the independent variable. Instead, the slope represents the odds ratio, the odds of given a particular x or a change in x, the odds of the odds ratio either increasing or decreasing a certain amount. So let's just briefly remind ourselves what odds are. And odds are the probability of an event divided by the probability of that event not occurring under a certain condition. So let's say you do not have glaucoma and you get an IOP, intraocular pressure, greater than or equal to 22. What's the probability of that? The probability of that is about 0.05. So the odds are the probability of 0.05, given you don't have glaucoma and you get a 22 or more, divided by 0.95, 1 minus 0.05. And that's an odds of 0.052. On the other hand, if you do have glaucoma, the probability of an IOP being 22 or greater is about 50%. So the odds are 0.5 over 0.5 or equals 1. So the odds ratio is the ratio of two odds under different conditions. In this case, the odds ratio of IOP being 22 or greater, given that you have glaucoma over don't have glaucoma, is 1 over 0.052 or 19. That means that if you have a IOP of 22, you're 19 times as likely to have glaucoma as not. We're going to explore this a little bit later, but that's what it says here. So our estimated risk is 19 times as likely. Now, an odds ratio is not a relative risk. It is an estimation of it. And you can get the relative risk with Bayes' theorem by taking the odds ratio divided by 1 minus prevalence, or plus prevalence times the odds ratio, divide that as the denominator, and that equals about 14. So we would, based on our slope and what we get at that point, we're going to estimate that the risk of having glaucoma is 19 times as great if you have a score of 22. Okay, now let's look at how logistic regression works to get at this. So the logistic regression looks just like a regular regression, y equals a plus bx. And when we get that b, we exponentiate it to give us our odds ratio. And the logit is the log of the probability over 1 minus p. That's that odds. It's the log odds. And when we solve for p to get the probability that you have glaucoma, then we would exponentiate our little formula. We exponentiate the whole thing and get e to the a plus bx over 1 plus e to the a plus bx. And the 50-50 cutoff point is simply solving for the probability being 0.5. So this, 0.5 over 1 minus 0.5, that's the log of 1, which is 0. And then 0 equals a plus bx, or x equals minus a over b. So we solve for x given that our probability of having glaucoma is at the threshold of 0.5. If you're higher than 0.5, we say you have glaucoma. If you're less, we say you don't. That's the predicted value. That's not what you actually have. All right, so let's work this out in a logistic regression problem. So here we have the BIVS database. And in that database, we have subjects who have, or patients who have had a TBI at some point in their life. So we have lots of TBIs. Then in this particular database, we had people who were either first or third year optometry students that have not had TBI. These are our controls. And then the BIVS is a 28 question questionnaire. And the summing those values up, we get the sum. So what we're going to want to do is see if we can use, or we'll use this total score to predict whether you're a TBI or a non-TBI. So let's do our regression. We go to Analyze, go down to Regular Regression as the type of statistic. We skip Linear. We come down to Binary Logistic. And our dependent variable is the category, TBI or not TBI. And the independent variable, here it calls it a covariate, is the sum. We usually like to save the probabilities just so we can draw a pretty curve, but for now we're just going to go on. So, okay. Now what that does is it gives us, tells us how many subjects we had. We had 264, and it's going to give the non-TBI a 1. So the higher the score, a positive coefficient means risk decreases. This is opposite of what we'd really probably like to have it. We probably could have set our categories so that 0 was non-TBI and 1 was TBI. That would have been preferred, but we didn't do that. It doesn't really matter. So, in this first thing, this is just looking at it without really just the this is kind of the denominator of our odds ratio. And then we look at various things here. Let's see, what do we have? Not too much informative here. Here we have what's equivalent to R-squared in regression. It's not exactly equivalent, but it's the best attempt to make it so that you can see something that would look like linear regression, because there is no R-squared in logistic regression. So there is this pseudo R-squared, the Cox and Snell and the Nagelkerke, and you can see they're not exactly alike, but they're showing this variance accounted for. In our classification table, this is the observed values. Our TBI, there were 107. 82 were classified correctly, that is, 82 were less than 50% on the score, probability less than P, because remember our 1 is non-TBI. And out of the 157 non-TBIs, 145 of them had a score greater than 0.5, and so were categorized correctly. But we missed 37. All right, now here is our equation. This is our y equals a plus bx. Let's copy this and put it into Excel. Here's a little worksheet I did to get the first slide up. All right, so here is our regression equation, a constant, y equals a plus bs. Logit of the p over 1 minus p equals a plus this constant, a is actually this value, plus b, this is b, times the individual score. So we had said before that from that formula that we just derived is that the 50th percentile is minus the constant divided by the slope, which in this case, oops, it doesn't like that. You don't want an equal sign there, not a space. And that is minus A divided by B. All right. Let's just, for the heck of it, let's go ahead and draw a graph. So our cutoff is about 38. So if we come in here, we draw a graph. I'm going to draw a scatter plot. Simple, define. Our y-axis is that predicted probability that we calculated. This is our model probability given the individual BIV score. It looks like this. So the higher the score, the lower the probability that you are a TBI. And again, we kind of did it backwards, so you can see. But if we were to come in here and do a cutoff, it's set at 0.5, so that's good. It's fine, so we can just close that. Then here is our score, and if we come to the vertical and we type in 39, was it 39 or 38? I don't remember. 38, sorry. Let's see, come in here. Make this a 38. You can see, you can see that it crosses right at the 50th percentile. So if you come up here, again, remember we're backwards. These are non-TBIs and these are TBIs. But never, in either case, 38 is our cutoff. So if actually in the BIV score, if you score greater than a 38, regardless of how we set up the logistic regression, if you score greater than a 38, you're predicted to have a TBI. And if you score less, your prediction is not. This is the threshold. All right. So the graph's a little confusing because it's going the wrong way because of our numbering system, our labeling system back here with the 0 and 1. But you still get the right, you get the answer, it just changes the sign. If we could make SPSS believe us that that was a plus 0.01, it would be the same thing. All right, that's it. In this video, we're going to discuss a little bit about logistic regression, what it is, and then we're going to use it to create a cutoff in a symptom score, specifically the brain injury system score, BIVS. And so here we go.